Welcome to the world of light and matter. Today we're exploring the fascinating phenomenon of the photoelectric effect. From its early discoveries to its modern applications, this concept has revolutionized our understanding of the physical world. And one man played a crucial role in its development, Albert Einstein. Let's dive into this amazing phenomenon, and then you can assess how impactful it has been in your own life. If subjects like this interest you, or if you think this could be useful to somebody you know, or even if this can serve as conversation starter to cause an impression, subscribe to our channel, share and like the video, and sit and wait for more cool stuff like this. Heck, you can even feel free to suggest something to talk about in the comments section, so let's wait no more. So, what is the photoelectric effect? Simply put, it's the process by which light is absorbed by a material, causing electrons to be emitted. But here's the fascinating part. The energy of the emitted electrons depends on the frequency, not the intensity, of the light. Albert Einstein's groundbreaking work in 1905 introduced the concept of wave-particle duality. He proposed that light behaves as both a wave and a particle, now known as photons. This idea challenged the traditional understanding of light and matter. Albert Einstein won the 1921 Nobel Prize in Physics for his explanation of the photoelectric effect, which was a major milestone in the development of quantum mechanics. Let us talk now about dual behavior of light, that is, its wave-particle duality. When we think of light as a wave, we can explain phenomena like diffraction, interference, and refraction. This wave behavior is essential for understanding how light interacts with matter in many situations. Here are some phenomena that the wave behavior of light can help to understand. Diffraction of the light. This is bending of the light, or any other wave, around obstacles. The diffracting object or aperture effectively becomes a secondary source of the propagating wave. It happens to all electromagnetic waves, and when the obstacle is similar in size to its wavelength, it is more remarkable. Interference. The interference of an electromagnetic wave, like the light, occurs when it is overlapped by another wave, creating patterns. Most people observe optical interferences on a daily basis, but don't quite know how this phenomenon actually occurs. An example that people can relate to is a film of oil on water or a soap bubble that reflects a variety of beautiful colors when natural or artificial light is shown upon it. This dynamic interplay of colors derives from the simultaneous reflection of light from both the inside and outside surfaces of the bubble. The two surfaces are very close together, only a few microns thick, and light reflected from the inner surface interferes both constructively and destructively. Refraction. Refraction is also commonly perceived by us all, although we may not know it is actually that phenomenon occurring. If diffraction is the bending of light around obstacles, refraction is its bending through media. Light slows down as it travels through a medium other than vacuum, such as air, glass, or water. This is not because of scattering or absorption, rather it is because, as an electromagnetic oscillation, light itself causes other electrically charged particles such as electrons to oscillate. The oscillating electrons emit their own electromagnetic waves which interact with the original light. The resulting combined wave has wave packets that pass an observer at a slower rate. The light has effectively been slowed down. When light returns to a vacuum and there are no electrons nearby, this slowing effect ends and its speed returns to be the famous 300,000 kilometers per second. Each existing material medium has its own physical characteristics, just like our fingerprints differ from one person to another. In simple words, physics and optics use a figure to distinguish one medium from another, and it is called the refractive index. On water, for instance, refraction occurs when light goes through a water surface, since water has a refractive index of 1.33 and air has a refractive index of about 1. Looking at a straight object, such as a pencil in the figure here, which is placed at a slant, partially in the water, the object appears to bend at the water's surface. This is due to the bending of light rays as they move from the water to the air. Once the rays reach the eye traces them back as straight lines, lines of sight. The lines of sight, shown as dashed lines, intersect at a higher position than where the actual rays originated. This causes the pencil to appear higher, and the water to appear shallower than it really is. So, thanks to the wave-like behavior of light, we can understand many phenomena that we normally use in our daily lives. Radio, television, eyeglasses, and much more, and are just few examples of the achievements we have thanks to understanding light as a wave. However, when we need to explain the photoelectric effect, we must consider light as a set of particles or photons. This quantum behavior is necessary to understand how light transfers energy to electrons and initiates the emission process. Wave equations that normally explain other wave and optics phenomena do not help to explain the photoelectric effect. Therefore, light consists of dual nature, which means sometimes it behaves like a set particles, known as photons, which explains how the light travels in straight lines. Sometimes light behaves as the wave, which explains how light bends or diffract around an object. It is like being a hypocrite. You act like a person for some people and circumstances, and like another person for other people or situations. Experiments by Hertz, Hallwachs, and Millikan confirmed Einstein's theory. They showed that the energy of the emitted electrons was directly proportional to the frequency of the light, not its intensity. This discovery led to a fundamental shift in our understanding of the physical world. Today, the photoelectric effect has numerous applications. Solar panels harness its power to generate electricity. Night vision goggles use it to amplify low-light images. And medical imaging techniques like PET scans rely on it to visualize the body's internal structures. The photoelectric effect has also led to a deeper understanding of material science and the behavior of electrons in solids. It's a testament to the power of human curiosity and the impact of fundamental research on our daily lives. Thanks for joining me on this journey into the world of the photoelectric effect. Remember, the intersection of light and matter holds many secrets yet to be uncovered. Subscribe to the channel, activate the little bell, like the video, and wait for more to come. Keep exploring, and who knows what wonders you might discover.